Welcome! In this session, we'll dive into solving LeetCode problem number 1536, minimum swaps to arrange a binary grid. This is an interesting grid-based problem that challenges us to think critically about row manipulation and optimization. Let's explore the problem, its constraints, and how we can approach it step by step. In this problem, you are given an n×n binary grid. Each row in the grid is sorted in non-increasing order, meaning all the ones in a row appear before any zeros. The goal is to determine the minimum number of swaps needed to rearrange the rows in the grid so that a specific condition is satisfied. For each row I, the number of trailing zeros in that row must be at least n1i. If it's not possible to meet this condition, you'll return -1. The input consists of the grid size n and the binary grid itself, and the output is the minimum number of swaps required or -1 if it's impossible. For example, consider a 3x3 grid where n is 3, and the grid is represented as follows. The first row is 0, 1, 0, the second row is 0, 0, 1, and the third row is 1, 0, 0. The output for this example is 3. To meet the condition, row 0 must have at least 2 trailing zeros, row 1 must have at least 1 trailing zero, and row 2 must have at least 0 trailing zeros. Initially, row 0 has 1 trailing zero, row 1 has none, and row 2 has 2 trailing zeros. To satisfy the condition, 3 swaps are necessary. Here's how the swaps happen. First, row 2 is swapped with row 1. Then, row 2, which is now at index 1, is swapped with row 0. Finally, row 1, now at index 0, is swapped with row 0. After these swaps, the reordered grid becomes 1, 0, 0, 0, 0, 1, 0, 1, 0. This new arrangement satisfies the required condition for trailing zeros in each row, and the total number of swaps performed is 3. Now let's look at another example. For a 3x3 grid where n is 3, the grid is 0, 0, 1, 1, 0, 0, 0, 1, 0. The output in this case is -1. To satisfy the condition, row 0 must have at least 2 trailing zeros, row 1 must have at least 1 trailing zero, and row 2 must have at least 0 trailing zeros. Initially, row 0 has 0 trailing zeros, row 1 has 2, and row 2 has 1. It's impossible to reorder the rows in a way that satisfies the condition because no row has at least 2 trailing zeros that can be placed at the top. Therefore, the answer is -1. In another example, suppose n is 2, and the grid is 1, 0, 0, 1. The output in this case is 0. To satisfy the condition, row 0 must have at least 1 trailing zero, and row 1 must have at least 0 trailing zeros. This grid already meets the condition. Row 0 has exactly 1 trailing zero, and row 1 has no trailing zeros. Since no swaps are needed, the answer is 0. To summarize the reasoning for this example, row 0 starts with 1 trailing zero, and row 1 starts with 0 trailing zeros. These values already satisfy the condition that row 0 must have at least 1 trailing zero and row 1 must have at least 0 trailing zeros. As the grid is already in the correct order, there's no need to perform any swaps, so the output remains 0. This highlights that not all grids require rearrangement. Finally, let's consider a few edge cases. For a single row grid, such as n equal to 1, the condition is always trivially satisfied since there's only one row, so the output is 0. In cases where it's impossible to satisfy the condition, such as when no row meets the trailing zero requirement for its position, the output is -1. For larger grids, such as when n equals 200, the solution must efficiently handle the input size. Additionally, if the grid is already sorted in a way that meets the condition, the output should be 0, as no swaps are needed. To tackle LeetCode problem number 1536, our goal is to ensure that in the grid, each row I has at least n×1 trailing zeros. This is the core condition for arranging the binary grid properly. One approach we can consider is the brute force method. The intuition behind this approach is straightforward. For each row, we count the trailing zeros, and if it doesn't meet the condition, we search for a valid row below it and perform incremental swaps to bring it into the correct position. The steps are simple. First, calculate the trailing zeros for every row and store this data in an auxiliary array. Then, iterate through each row, verify if it meets the required condition, and if not, look for a suitable row below and swap step by step. During each swap, we record the number of operations. While this method is conceptually easy to implement, it involves nested iterations, leading to a time complexity of n squared, which can become inefficient for larger grids. The brute force approach, despite being simple, has a significant drawback. The repeated row swaps introduce inefficiencies, especially as the grid size grows. To address this, we can use an optimized greedy approach. This strategy eliminates redundant swaps by directly calculating the minimum swaps needed. The key here is to use the trailing zeros array to identify the first valid row below the current one and bring it into position with minimal movements. The steps for this approach are as follows. First, pre-compute the trailing zeros for all rows and store them in an array. Then, iterate through the rows, verifying if the condition is met for each one. If a row doesn't meet the condition, find the nearest valid row below, calculate the swaps required to bring it up, and adjust the grid by shifting the intermediate rows. This adjustment updates the trailing zeros array accordingly. While the overall time complexity remains n squared, this method reduces redundant operations, making it much more efficient in practice. It also balances performance and simplicity, avoiding the overhead of unnecessary rechecks and swaps. The optimized greedy approach stands out as the preferred strategy due to its combination of efficiency and clarity. By directly calculating the necessary swaps and minimizing intermediate movements, it avoids the inefficiencies of the brute force approach while maintaining a manageable n squared complexity. The pivotal realization here is that the problem can be reframed as finding the first valid row for each position and minimizing the movements required to bring it there. This insight simplifies the solution and streamlines the process. Additionally, using an auxiliary array to track trailing zeros enables us to make decisions quickly without recalculating values repeatedly. When comparing the two approaches, the brute force method, while simple, involves excessive swaps and is impractical for larger grids. The greedy approach, on the other hand, leverages direct calculations and minimizes operations, making it significantly more efficient without introducing unnecessary complexity. The optimized greedy solution was chosen because it achieves the right balance between clarity and efficiency. It adheres to the constraints of the problem, avoids redundant computations, and remains straightforward to debug and implement. With a time complexity of n squared, it is well suited for the given grid size constraints and performs effectively in practice. This approach focuses on directly addressing the problem's requirements, minimizing the number of swaps while ensuring the grid meets the trailing zero condition. By avoiding overly complex alternatives and prioritizing simplicity alongside efficiency, this solution provides a clear and practical pathway to solving the problem. In this problem, we need to transform a binary grid into a valid configuration using the fewest row swaps. A grid is valid if, for each row at index I, the number of trailing zeros in that row is at least n(1), where n is the size of the grid. To solve this, we follow a series of systematic steps. First, we parse the input, which is a square binary grid of size nxn. Our goal is to determine the minimum number of swaps required to achieve a valid grid configuration. If it's impossible to make the grid valid, we return -1. The key insight here is that the number of trailing zeros in each row determines if the row satisfies the condition. By focusing on trailing zeros, we can simplify the problem and guide our row swaps more effectively. Next, we pre-compute the number of trailing zeros for each row by traversing the grid and storing these counts in a trailing_zeros list. This list will be central to our approach, as it captures the information needed to evaluate and rearrange the rows. Now, we iterate through the rows of the grid to ensure the validity condition is satisfied for each one. For a row at index I, the required number of trailing zeros is n(1). Our task is to check if there's a row at or below the current index with at least this many trailing zeros. If no such row exists, it's impossible to rearrange the grid, and we return -1. If we find a suitable row, we move it to the current position, counting the number of swaps required. The number of swaps is simply the distance between the row's current position and the target position. After performing the swap, we update the trailing_zeros array to reflect the new order of rows. Once all rows have been processed, the total number of swaps gives us the result. At the core of this process is the greedy approach. By always bringing the closest valid row to the current position, we minimize the number of swaps. This ensures an efficient solution. However, we must account for edge cases where no row satisfies the condition, as this would immediately result in an answer of -1. If multiple rows meet the condition for a given position, choosing the closest one is essential because it minimizes the number of swaps. To manage the data efficiently, we use a simple array, trailing_zeros, to track the trailing zero counts for each row. This abstraction allows us to focus on comparisons and swaps without directly modifying the grid. The grid itself remains unchanged, only the order of rows is manipulated. In terms of complexity, computing the trailing zeros for all rows takes n² time because we have to traverse each row of the grid. For each row, finding a suitable row to swap involves scanning the remaining rows, which takes n in the worst case. As a result, the overall time complexity of the algorithm is n². The space complexity is n, because we use the trailing_zeros array to store the trailing zero counts for all rows. This is an efficient and straightforward way to solve the problem, leveraging the simplicity of greedy algorithms and auxiliary data structures. The implementation begins by calculating the trailing zeros for each row. For each row in the grid, we count zeros starting from the rightmost element and stopping as soon as we encounter a1. These counts are stored in the trailing_zeros list. Next, we iterate through the rows to perform the greedy swaps. For each row at index I, we calculate the required number of trailing zeros as in I1. Then, we search for the closest row below or at the current index that meets this requirement. If no such row exists, we return -1 since it's impossible to make the grid valid. If a suitable row is found, we calculate how many swaps are needed to bring it to the current position. These swaps are performed by shifting the rows in the trailing_zeros list, ensuring the array reflects the new order. We accumulate the total number of swaps during this process, which is returned as the result after all rows are processed. Let's go through an example to see how the algorithm works in practice. Consider the input grid 0, 1, 1, 1, 0, 0, 0, 0, 0. First, we compute the trailing_zeros array, which gives 0, 2, 3. For row I equals 0, the required number of trailing zeros is 2. Row 1 satisfies this condition, so we swap row 1 with row 0. This updates trailing_zeros to 2, 0, 3. Next, for row I equals 1, the required number of trailing zeros is 1. Row 2 satisfies this condition, so we swap row 2 with row 1. This updates trailing_zeros to 2, 3, 0. Finally, for row I equals 2, the required number of trailing zeros is 0, which is already satisfied, so no swap is needed. The total number of swaps performed is 2, which is the result. This example demonstrates how the algorithm efficiently rearranges the rows to achieve a valid grid while minimizing swaps. Here, we start by defining our solution within a class, which is standard practice for LeetCode problems. The main function, minSwaps, takes the grid as input and begins by determining the size of the grid. Next, we define a helper function count_trailing_zeros, which is crucial for our logic. This function counts the number of zeros at the end of a given row by iterating backward through the row. If it encounters a 0, it increments the count. If it encounters a 1, it stops counting. This helps us identify how many trailing zeros each row has, which is important for determining if a row can meet the requirements of a valid grid. Using this helper function, we calculate the trailing zeros for all rows in the grid and store them in a list called trailing_zeros. Now, we initialize a variable swaps to 0. This will keep track of the total number of swaps needed. The goal is to ensure that each row satisfies the condition of having at least as many trailing zeros as its position from the bottom, starting with the last row. To achieve this, we iterate from the bottom row upwards, represented by the variable target. For each target row, we look for any row in trailing_zeros that has the required number of trailing zeros. Once we find such a row, we mark it as found, add the number of swaps needed to move it up, and remove it from the list to simulate shifting the rows. This process ensures that we progressively build the grid into a valid state. If we fail to find a row with enough trailing zeros for the current target position, it means the grid cannot be rearranged to meet the requirements, so we return -1. This indicates that the task is impossible given the initial state of the grid. However, if we successfully process all rows, we return the total number of swaps calculated. This approach ensures that the grid is validated systematically, and we minimize the number of operations needed to arrange it. By carefully managing the trailing_zeros list and updating it as we go, we maintain an efficient solution that solves the problem within the constraints. Here, we begin by importing the necessary Java utilities and defining our class. The main function we're focusing on is minswaps, which takes a 2D integer array grid as input. The grid represents a binary matrix where we need to ensure that for each row, the number of trailing zeros meets the requirements for a valid binary grid. First, we calculate the length of the grid, which will help us iterate through the rows and manage our logic. Next, we define a helper function, countTrailingZeros, which takes a row as input and calculates the number of zeros at the end of that row. This function is essential because trailing zeros determine whether a row meets the necessary constraints. Within the helper function, we loop backward through the row and count zeros until we encounter a 1, at which point we stop counting. This count is returned for each row. After defining the helper function, we initialize an array, trailing zeros, to store the count of trailing zeros for each row in the grid. Using a loop, we populate this array by passing each row of the grid to the countTrailingZeros function. Finally, we initialize a variable swaps to 0, which will keep track of the total number of swaps needed to make the grid valid. Now, we shift our focus to processing the rows to ensure the grid becomes valid. Starting from the bottommost row, represented by the target index, we check if there's a row above it with enough trailing zeros to satisfy the constraints. This is done using a loop to iterate through the trailing zeros array. If a suitable row is found, we mark it as valid and calculate the number of swaps required to bring it to the top of the grid. Swapping is simulated by shifting all the rows between the current position and the top downward, while the selected row is moved to the top. This reordering is achieved using a temporary variable to store the current row's trailing zero count, and then we adjust the trailing zeros array accordingly. If no row meets the requirements for the current target, we know it's impossible to make the grid valid, so we return -1. After processing all rows successfully, we return the total number of swaps. This ensures that the grid meets the necessary conditions with the minimum number of operations, achieving the desired result efficiently. To solve this problem, we start by analyzing the given grid and calculating the number of trailing zeros in each row. For the first row, 0, 0, 1, there are no trailing zeros because the last digit is a 1. For the second row, 1, 1, 0, the trailing zeros count is 1 since there is 1 0 at the end. Similarly, for the third row, 0, 1, 0, the count of trailing zeros is also 1. This gives us a trailing zeros array of 0, 1, 1. Next, we need to rearrange these rows so that the grid satisfies the condition where each row has at least as many trailing zeros as the row index from the bottom up. For the bottommost row, which corresponds to a target of 2 trailing zeros, no row in the grid has enough zeros to meet this requirement. Since it's impossible to satisfy the condition, we return -1 as the output. Now, let's look at another example grid and repeat the process. For the first row, 1, 0, 0, there are 2 trailing zeros. For the second row, 0, 1, 0, there is 1 trailing zero. Finally, for the third row, 0, 0, 1, there are no trailing zeros. This gives us a trailing zeros array of 2, 1, 0. To satisfy the condition, we start with the bottommost row, which requires at least 2 trailing zeros. Row 0 already meets this requirement, so no swaps are needed. We then move to the second to last row, requiring at least 1 trailing zero. Again, row 0 meets this condition, so no swaps are necessary. Finally, the top row requires 0 trailing zeros, which is already true for row 0. Since no swaps were required throughout this process, the total number of swaps is 0, and we return 0 as the output. In the final example, we begin by computing the trailing zeros for each row. For the first row, 0, 0, 1, there are no trailing zeros. For the second row, 1, 0, 0, there are 2 trailing zeros. For the third row, 0, 0, 0, there are 3 trailing zeros. This results in a trailing zeros array of 0, 2, 3. We then rearrange the rows to meet the condition. The last row requires at least 2 trailing zeros. Row 1 satisfies this condition, so we swap it to the top, resulting in 1 swap. The updated trailing zeros array becomes 0, 3. Next, the second to last row requires at least one trailing zero. Row 0 only has 0 trailing zeros, which is insufficient, so we swap row 1 to the top again, making it 2 swaps in total. The trailing zeros array is now 0. Finally, the top row requires 0 trailing zeros, which is already met, so no further swaps are needed. The total number of swaps is 3, and we return 3 as the output. Here, we analyze the time complexity of the solution step by step. First, consider the pre-processing phase where we calculate the number of trailing zeros for each row. Since the function count_trailing_zeros processes n elements in each row and is called for all n rows, the total work for this step is O n multiplied by O n, resulting in O n squared. Next, the outer loop runs 4 n iterations, corresponding to each target row from n1 down to 0. Within this outer loop, there's an inner loop that finds a valid row with enough trailing zeros. In the worst case, the inner loop iterates over all rows in the trailing_zeros list, which initially has n rows, and decreases by 1 row in each iteration of the outer loop. The total number of iterations across all runs of the outer loop is the sum of the first n natural numbers, which simplifies to O n squared. Adding everything up, the total time complexity of the solution combines the pre-processing step, which is O n squared, and the work done by the outer and inner loops, which is also O n squared. This gives us an overall time complexity of O n squared. Now, let's examine the space complexity. The input grid itself, which is of size nxn, is given and does not count as additional space usage. The trailing_zeros list, which stores one integer per row, requires O n space. Finally, other temporary variables like count, found, and swaps only use constant space, or O1. Adding all these considerations together, the total space complexity is O n, primarily due to the trailing_zeros list. To put this into perspective, let's compare this optimized solution to a brute force approach. A naive solution would involve generating all possible permutations of the rows in the grid and then checking each permutation to see if it meets the condition. Since generating permutations involves O n operations, and checking each permutation would take O n squared, the total complexity for the brute force approach would be O n n squared. This becomes computationally infeasible for larger values of n. In contrast, our optimized approach avoids this explosion in complexity by using a greedy strategy to select rows based on their trailing zeros, reducing the complexity to O n squared. In conclusion, the time complexity of this solution is O n squared, and the space complexity is O n. While this approach is efficient for moderate values of n, such as up to 200, it may face performance challenges for very large grids due to the quadratic time complexity. Nonetheless, this optimized solution is significantly more practical than a brute force method, making it a robust choice for the problem. One common mistake when solving this problem is miscounting the trailing zeros in each row. Instead of focusing on the total number of zeros in the row, you need to specifically count the zeros at the end of the row, as only trailing zeros impact whether the row satisfies the condition. To avoid this, use a loop that starts at the end of the row and counts zeros until a 1 is encountered. Another mistake is attempting to sort rows directly based on their trailing zeros. While this might seem like a shortcut, it violates the constraints of the problem, which require row swaps rather than reordering. The correct strategy is to find the first row below the current one that meets the trailing zero condition and then swap it upward. Finally, it's easy to overlook the importance of tracking the swap cost. Each swap represents 1 unit of cost, so you need to carefully increment the swap count for every upward movement to ensure you calculate the total cost accurately. Another issue to watch out for is assuming that the input grid is always valid. Not all grids can be rearranged to meet the conditions, and failing to handle these cases can lead to runtime errors. For example, if no row has enough trailing zeros to satisfy the requirement, a valid configuration is impossible. You should include a check for this and return an appropriate result, such as -1. Additionally, avoid using a brute force approach to solve the problem. While trying all possible row permutations might seem like a comprehensive solution, the factorial growth in time complexity makes it infeasible for larger grids. Instead, a greedy approach is much more efficient. By always swapping the first valid row upward, you minimize the number of swaps and solve the problem within a reasonable time frame. To excel in interviews, it's helpful to focus on key patterns within the problem. One of the most important concepts is that row I must have at least n(i)(1) trailing zeros to meet the requirements. Breaking the problem into this specific condition simplifies the logic significantly. The greedy approach is ideal here, as it ensures that you minimize the swap count by always moving the first valid row upward. This strategy is both efficient and straightforward. It's also crucial to handle edge cases effectively. These may include rows with no trailing zeros, grids where it's impossible to satisfy the condition for all rows, and trivial cases like single row or single column grids. Being prepared for these scenarios demonstrates a strong understanding of the problem and ensures your solution is robust. This problem shares similarities with several other challenges on LeetCode, making it a good opportunity to practice related concepts. For instance, in problem 1353, maximum number of events that can be attended, you also use greedy logic to optimize outcomes. Problem 406, queue reconstruction by height, involves rearranging elements within a grid-like structure based on specific constraints, which is conceptually similar. Problem 927, 3 equal parts, focuses on binary arrays and requires careful handling of conditions, much like counting trailing zeros here. Finally, problem 763, partition labels, emphasizes breaking a problem into partitions using a greedy approach. Exploring these problems can deepen your understanding of patterns and techniques applicable to minimum swaps to arrange a binary grid. When considering alternative approaches, the greedy method stands out as the optimal solution. It has a time complexity of O(n) squared, due to the nested loops used to find and swap rows, and its space complexity is O(1), as no additional data structures are needed. This makes it both efficient and straightforward to implement for moderate grid sizes. On the other hand, a brute force approach is highly inefficient, with a time complexity of O(n)(n), due to the need to generate and validate all permutations. Its space complexity is also high, as storing these permutations requires significant memory. While brute force might work for very small grids, it's impractical in real-world scenarios or interviews. A more advanced option is to incorporate binary search to optimize the search for valid rows. While this can reduce search time, it adds complexity to the implementation. Each approach has its trade-offs, but the greedy method strikes the best balance between efficiency and simplicity for this problem. Great work! We've reviewed the solution to LeetCode number 1536, minimum swaps to arrange a binary grid. This problem highlights the importance of greedy algorithms and efficient row manipulation. Keep practicing these techniques for grid-based problems, and stay motivated on your coding journey. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!